Okay, this is topic 42, extreme values and local extrema. So you can read all this on your own, but basically what it amounts to, you have an absolute maximum if you have between A and, in this case, F, right? They could have picked a different point for that, but you have an absolute maximum if that is the highest y value on that function. And you have an absolute minimum where you have the least or the smallest y value, including the endpoint. So for example, if you're looking at this, it's kind of hard to tell, but I think this one is the absolute minimum on this, all right? Now, remember that on this one, the absolute max or min could also be located on the endpoint. So if this endpoint happened to be lower than this minimum, then that would be the absolute minimum would be located right there, okay? Now, a relative or local max or min for that matter, that's where you have something like this. I mean, this is a minimum, but it's not the absolute minimum because there's a smaller, this one has a higher y value than this one. Does that make sense? So you can even look at the picture. This one's higher than that one. So that's the idea. When you see the picture, it makes a whole lot of sense. Okay, so now we're gonna go over example 1. Now example 1 really has nothing to do with this, so it's just I'll review what we did in topic 41. So I'm going to quickly go through example 1 and 2. Okay, so in this one they're asking us to find the critical values. And if you remember from the last lesson, the critical values are located when the derivative is equal to 0. Okay, so that happens when the derivative, whatever point the derivative is equal to 0, or actually and, if that happens, if you have any point where the derivative is undefined or does not exist. All right, so those are the critical values. So I have to first take the derivative of this. I'm going to use the power rule. So that's 48x squared plus 36x. All right, so right now all I have done is taken the derivative of that. So now to figure the critical values, I'm going to have to set my derivative equal to 0. Which means I have to set this equal to 0. And then I have to solve for it. Now obviously if the problem is pretty difficult, you can use your calculator, but you should at least try to solve it with that at first. Okay, so now notice that I have a common factor of 12x. So I have x squared minus 4x plus 3. That's equal to 0. So now it looks like I'm able to factor this. All right, so I have 12x, x minus 3, x minus 1 is equal to 0. So now I'm going to set each factor equal to 0, including that one. Remember, this is a factor also. So I have 12x is equal to 0, x minus 3 is equal to 0, x minus 1 is equal to 0. So therefore I have 3 values. 3 critical values. And on this one, we don't have an interval, so I guess all of these are going to have to be. And then now also, before I do anything else, I have to kind of come back over here and figure out if there's anywhere where the derivative does not exist or is undefined. Is there anywhere on the derivative function, and you can see the derivative function is some kind of cubic where this is undefined. So think of this, is there anywhere, all right, where you have any type of vertical, any breaks or anything like that on here really? If you're looking at this one, if you're looking at the graph of this one, is there anywhere where you have a sharp point, a cusp, or a vertical tangent line? And there's not. Okay, so in this one, this is, if you think about it, this is a function to the power of 4. You should know sort of what it looks like, and you should know also that there is no breaks in this instance. There is no breaks, no sharp points, and no vertical tangent lines. Okay, so this is none. There's not any place where the derivative is not defined. So therefore, because of that, my critical values are located at x is equal to 0, x is equal to 3, and x is equal to 1. And that is my answer for that one. All right, now I'm going to quickly go through number 2. Same idea. I'm looking for the critical value, so I'm going to take the derivative. Now notice that on this one, you really have a choice on how you want to do this. You can try to do the product rule if you want to, but I've noticed very quickly that I can actually distribute here. Alright, so I'm going to try to distribute here. So 4 times x to the 3/5, so all that's just 4x to the 3/5. Okay, and this is going to be minus. Now x times x to the 3/5. Remember, we're going to add the exponents. Alright, so if I add a 1 plus 3/5, well, that would be the same thing as 3/5 plus 5 over 5. That is going to give me 8 over 5. Now again, if you'd rather do the product rule, by all means do it. Alright, it'll give you the same answer. Maybe it might be even easier. I don't know. So at this point, now I'm going to take the derivative, and I'm going to set it equal to 0. So let's see, this is going to give me, well, that's definitely not going to give me 4. It's going to give me 4 times 3/5. So I'm going to go ahead and write it. So it's going to give me 12 over 5, x to the negative 2/5, minus this one right here is going to give me negative 8/5, x to the 3/5. Okay. So now at this point, I'm going to simplify a little bit. Now at this point, what I'm going to do here is I'm going to find a common denominator. Only to make this easier, you don't necessarily have to do this part, but I'm going to go ahead and do it. I'm going to find a common denominator so I can have one fraction. So this step is not necessary, but I want to be able to look at this in a more simple manner. So I'm going to multiply top and bottom by this denominator, okay, since I already have a 5 in common. So when I do that, let's see, that's going to give me 12 minus, if I multiply x to the 3/5 times x to the 2/5, remember I add the exponents, right? So 3/5 plus 2/5, well, that's 1. So this is going to be 8x to the first power, but I'm not going to write the first power, over the common denominator, which is now 5x to the 2/5. Alright, so that's just the derivative. Now I have to set the derivative equal to 0. Okay, I set the derivative equal to 0, so I have 12 minus 8x over 5x to the 2/5 is equal to 0. Okay, so I'm going to try to figure that out. Now I'm going to cross multiply. I'm going to have 12 minus 8x is equal to 0. Alright, and then at that point, I'm going to solve for x. Now when I solve for x, I get that x is equal to, let's see, subtract the 12 divided by negative 8. Let's see. Okay. I'm going to have 3/2. Right, so x is equal to 3/2. So that's one of my critical values. Now, on the other side, I also have to set my derivative. Don't forget, I have to set my derivative. I have to figure out where my derivative does not exist or is undefined. Okay, so same idea, really. I can set this equal to 1 over 0. If you just look at it also, right, this x doesn't matter, but what matters is what's going to make this denominator 0, which is 0 ahead of time, but if you don't see that, that's fine. Set that up like that and then cross multiply. So you would have 5x to the 2/5 is equal to 0, so x is 0. So notice that on this one I actually have two critical values. Now I'm wondering what that looks like. I really don't know. Okay, so I have 3/5, oh sorry, 3/2, and also at 0. So I have two critical values. Okay. Now before we go on, let me just go ahead and graph that. I'm kind of curious to see what that looks like. Let me see what this looks like over here. So x to the 4 minus x. Just curious what it looks like because I really don't know. Alright. Interesting. I guess that's your vertical tangent right there. And then you have another maximum right there. So those are two critical values. But anyway, now I'm going to go ahead and go to the back. Now this one's more related to the stuff we talked about, all right, at the beginning of the lesson. All right, so we're going to try to find the derivative. We're going to do the derivative test for the local extrema. Okay, so I'm actually just going to write this down, and you can read this in the end if you like, okay? And then we're going to go for that. So the first thing I have to do is I have to find my critical point, so I have to find the derivative. All right, so my derivative in this case would be 3x squared. Remember, I'm taking the derivative of this. I'm going to set that equal to 0 to figure out my critical value. So it starts off pretty much the same. Okay. Now when I solve for this, I'm going to add the 12 divided by 3, which will give me x squared is equal to 4. Then I'm going to take the square root, which will give me plus or minus 2. However, negative 2 is not in the interval. And the interval, it happens to be right here. So notice that negative 2 is not in this interval. So that's why I'm not going to include negative 2. So the only critical value that I have right now is negative 2. Okay? I'm sorry, positive 2. So now the other thing that I'm going to do is I'm going to try to figure out where is my derivative undefined. All right, and if either you can look at this one and think, okay, is there any cusp, sharp points, or vertical tangent lines, and there's none. So this is none. All right, is defined everywhere. So now what I have to do is I have to figure out to check, and that's what they mean with evaluate f of x for each local extremum and evaluate f of a and f of b for comparison to identify the absolute maximum or minimum of or minimum output value. So really what that means is, remember what I said earlier at the beginning, your max or mins can be located on the endpoints, and that's the important thing. Okay, so I don't know what that looks like yet. I mean, I sort of have an idea what that looks like, but I don't know everything about it. So what I have to do is I'm going to have to check the endpoints. We're going to check the endpoints and the critical values. Okay, so by that I mean what I'm trying to do here is, now that I have the endpoints, is I'm going to plug the endpoints back into the original function, and I'm gonna be looking at the y values. All right, so if I plug in a negative 1 back into the original function, that's going to give me a positive 11. All right, and I'm also going to check the other endpoint, which was 3. Now when I plug in that 3 back into the original, this is going to give me a negative 9. And then finally what I have to do is I have to plug in my critical value, which in this case, my critical value, if I plug it in here, that's going to give me a negative 16. Okay. Now look at the y values. Don't worry about this. Just look at the y values. Which one is the biggest y value? All right. The biggest y value is going to be this one. All right. So I actually have an absolute maximum located at negative 1, 11. All right. Notice that. How do I know it's a maximum? Because I have the biggest y value. All right. Now similarly, my absolute minimum is going to be located at my smallest y value. If you look at all these 3 points, which one has the least, which one has the smallest y value? And the smallest y value happens to be this number. All right, so my absolute minimum is going to be located at 2, negative 16. Okay, so that's what that's going to look like. All right, so not to lose I don't want to lose track of what we're doing, all right? Remember, the absolute maximum or minimum, we are talking about the graph of f of x, all right? And we do all this derivative stuff just to figure out if we have a max or minimum and for the critical points, okay? Once you check them, once you check the endpoints and all your critical values, you're just going to look at the y values you get out of those. And the biggest y value is going to be your maximum, your smallest y value is going to be your minimum, all right? So now let's go ahead and take a look at example 4, same idea, right? We're going to take the derivative, set it equal to 0 to figure out our critical values. So this one right here would be negative cosecant x cotangent x. Okay, so now what I'm going to do now, what I'm going to do here is I'm going to set my derivative equal to 0. And I'm also going to set my derivative. I want to figure out where my derivative does not exist. Alright, so this one really, if we're looking at derivative, we have a break here. Now, if you look at the graph of the cosecant in this interval, don't forget you're looking at the cosecant in that interval. Okay? Really what I'm looking for if I graph that, and I haven't really even looked at it, but let me just quickly look at it. Cosecant is 1 over sine. So 1 over sine x. I'm going to change my window to pi over 6 minimum. And then pi over 3 for this one, for the maximum. Alright, so that'll at least help me on the window. Now what I'm really looking for, and this might not be the greatest of graphs here, but I'm looking to see if there is either a maximum or minimum that you can see here. I really can't tell if there is one. This is really hard to tell. But I'm also looking to see if I have any sharp points or cusp or anything like that, and it looks like I don't. Alright, so also if you wanted to, you can also graph, this would be the derivative, right? This would be the derivative. Now I'm looking to see if the derivative is ever equal to 0. So meaning on this, if I look at this window again, I have to change my window. Yes. So when I change that window, I'm trying to see if it ever crosses the x-axis between in that interval, then the derivative will be equal to 0, and it doesn't. Okay. And on this one, there is no breaks in this. Okay, so if you see some kind of vertical asymptote there, then that will mess everything up. So therefore, on this one, graphing over that interval, so I'm going to write it here. Graphing over interval pi over 6 to pi over 3. You find no values where the derivative is equal to 0 and no values where g prime of x does not exist or is undefined. Alright, so that's basically what we just did in the calculator. So therefore, because we have no critical values, so we have no critical values here, so therefore all we can check, we can only check the endpoints. Only because we have no critical values. Alright, so we're going to check the endpoints. So I have to plug in this endpoints into the original function. So this would be cosecant of pi over 6, which would be the same thing as 1 over sine of pi over 6. Okay. And this one, let's see, sine of pi over 6 would be 1/2. Yes, so it would be 1/2, so 1 over 1/2, this would be equal to 2. Okay? And on this one, the cosecant of pi over 3 is equal to 1 over sine of pi over 3. Sine of pi over 3 is square root of 3 over 2, so this is 2 over the square root of 3. Alright, so at this point you just have to figure out which one's the smallest one and which one's the biggest one. Alright, so you have to basically figure out 2 divided by this is obviously going to be less than 2, correct? Because we're dividing 2 by some number, even if you're not sure what the number is, this number is going to make that smaller than this. So therefore my absolute maximum is going to be located at pi over 6, because this is the biggest y value here. And my absolute minimum is going to be located at pi over 3, because this is the smallest y value. Alright, this is a little bit labor intensive, but the idea is easy. If you have any questions, let me know.